Okay, so now this looks more like what we would expect in this part of the exam. Okay, it's a system, so remember the first thing that we're going to do, we're going to find the eigenvalues and eigenvectors. So we've got 3 minus lambda, minus 4, 1, minus 1, minus lambda. This is equal to lambda plus 1 times lambda minus 3 plus 4. And then when you sort of expand this, this is lambda squared minus 3 lambda plus lambda. So that's minus 2 lambda. And then we have minus 3 plus 4. So that's plus 1. And notice this is lambda minus 1 squared. Okay, so we just have one eigenvalue. Okay, and now we're going to find the eigenvectors. We've got 3 minus 1, minus 4, 1, minus 1, minus 1, times xy. Set this equal to 0, 0. So the top equation is 2x minus 4y equals 0, and the bottom equation is x minus 2y is equal to 0. Okay, so notice that the bottom equation, or the top equation, is 1/2 the bottom equation, indicating that we've done things correctly most likely. X equals 2y is what the bottom equation says. Okay, so this means that any vector where the top entry is 2 times the bottom entry is going to be an eigenvector, except for the 0 vector. Okay, so now notice here there's just one linearly independent eigenvector. So whenever we have the case of a repeated eigenvalue and one linearly independent eigenvector, we have to find the generalized eigenvector. And to do that, we're going to solve an equation that is very similar to this one, except instead of having the 0, 0 vector there, we're going to have the eigenvector there. And the solution to that equation is the generalized eigenvector. And so for us, this is 2 minus 4, 1, minus 2 times xy is equal to 2, 1. The top equation says 2x minus 4y is equal to 2, and the bottom equation says x minus 2y is equal to 1. Again, observe that the top equation is 2 times the bottom equation, indicating that we have done things correctly here. Okay, and so the bottom equation says x is equal to 1 plus 2y. So any vector where the top entry is 1 plus 2 times the bottom entry, so something like this, just to be a little explicit, any vector of this form, except for the 0 vector, is going to be a generalized eigenvector. I'm going to take s is equal to 0, and we get 1, 0. So this is a generalized eigenvector. Okay, and in this case, the general formula in this case, where you have a repeated eigenvalue and only one linearly independent eigenvector, is x of t is equal to c1 e to the lambda t v plus c2 e to the lambda t tv plus w. That's the general solution. I mean, you know, for like arbitrary v, w, and lambda. The general solution to this problem, for our particular problem, is equal to c1, lambda is equal to t, is equal to 1, right? So c1 e to the t times v1, which is 2, 1 plus c2 e to the t times t v1 plus w, which is 1, 0. Okay. And that is it for this problem. Now I'm going to actually go ahead and do the second problem, or problem 4, because problem 4 is to find a particular solution to this problem. Okay, notice that the matrix stays the same. The only thing is that we have an initial condition. Okay, so the general solution is x of t is equal to c1 e to the t 2, 1 plus c2 e to the t t 2, 1 plus 1, 0. Now I want to figure out what c1 and c2 are, and I use the initial condition there. So when t is equal to 0, this says x of 0 is equal to 1, 0, and then we've got c1. Okay, e to the 0 is just 1, so this is 2, 1 plus c2. What's going on in the brackets here? Well, if t is 0, this part is equal to 0, and so we're just left with 1, 0. Okay, so we've got two equations. One is equal to 2c1 plus C2. That's what the top equation says. And 0 is equal to C1, and then it's going to be plus 0 C2. So it's just going to be plus 0 C2. So this implies that C1 is equal to 0. We plug that into the top equation. This implies that C2 is equal to 1. And so the solution to this initial value problem is x of t is equal to e to the t times t 2, 1 plus 1, 0, like that. And there you have it, two questions in one video.